Well, good evening, everyone. Thank you so much for joining us. We are representing proximitE Inc. My name is Christiena Paulette. I am the Chief Financial Officer, and I'm joined this evening by my good friend and the CEO of proximitE, Richard Nederlander.
Hello. Yeah, so I'm the CEO. We're going to start this presentation basically by explaining the startup itself, and then we're going to go into the science and the engineering behind high-altitude rocket launches. So just for a bit of background, I graduated from Columbia University with a degree in astrophysics. I am currently an electrical engineer in Vanderbilt University. It's my graduate studies, and my research is in studying how radiation impacts space-based electronics.
And I also went to Columbia. That's actually where we met and formed this idea. I graduated the same year as Richard, and I had a degree in political science and business management. And upon graduation, I accepted a full-time offer as a commercial banker on Park Ave, and specifically focusing on enterprise valuation at a bulge bracket bank.
So just to get us started, I'm going to talk about the inspiration for proximitE. First of all, what even is it? So proximitE's mission is to launch rockets, small, lightweight rockets from high-altitude balloons. And the inspiration from this comes from a summer of research I did as an undergraduate. I helped the Vanderbilt satellite team build the satellite, and they were going to test the satellite before launching on an actual rocket by just floating on a balloon, just to see how it responds to the radiation in the atmosphere. But unfortunately, as it was on the balloon exploded, and we lost that satellite, and it just inspired me. It made me think, like, okay, what went wrong here? Why did this balloon explode? What can we do to make it different? Because the reasons for choosing a balloon over a rocket were financial. It's much more affordable to first test your satellite by just using a balloon. Like, helium isn't that expensive at all. Comparison to a rocket, it's $10,000 per pound, but that's when you're on a really large rocket already, and they usually request you have multiple tons already on your satellite. And so proximitE from this was born. I did research into just the cost effect of launching your rocket from above Earth's atmosphere, because as it turns out, most of the fuel requirements of a rocket are from the rocket going through the atmosphere. The atmosphere is really thick. Rockets, in fact, have to be engineered specifically to pierce through the atmosphere.
Exactly. So as Richard touched upon, we identified a unique problem, not only for the sake of having an interesting challenge to solve, but also one that would create unique synergies environmental-wise and also to meet a demand in the market. So spaceflight companies were unable to meet this demand for small satellite launches because of the problems that Richard outlined. It was very costly, and most of the cost wasn't even going into the actual satellite itself. It was going to just getting it off the ground. So how do we overcome that? Well, we have to figure out how to keep the costs down and forcing spaceflight companies to focus on medium to large satellite launches. Mm-hmm. And with this, the solution. So our method will drop the price per pound for small rocket launches by over half. Now that's a sizable amount. We will decrease the amount of fuel required to 10% of the total mass of the rocket, as opposed to the industry standard as right now, 90% of the total mass.
And that's important to note. So most of what's on a rocket is the fuel to just get off the ground, 90%. And this is just the reason we continue to use this traditional means of launching rockets from the ground. It's just because it's been tested throughout decades since the 1940s. People haven't really been innovating on this technology because this is just the standard. It's been tested, but it's really cost inefficient, fuel inefficient. Just you name it. It's just not the best options out there.
So this is a visual representation of what our prototype would look like.
Very basic diagram.
Keep it simple because it's supposed to be something that is a bit more simple than the current process in many ways. And from this, we have a more detailed blueprint of it, which I'll let Richard get into.
Yeah, so we have the rocket itself in the center of this cube. Everything about this would be lightweight. There's been a lot of innovation in material science that's been just decreasing the amount of weight, like for fabrics, for tethers, for metals, all of that, all of those masses are just going down. Mm-hmm. And we are able to utilize that research in constructing a concept for these high altitude rocket launches.
So the pricing model. So how are we going to make this innovative idea in this industry that's ripe for disruption actually a reality? Well, we would have yearly and bi-yearly contracts to customers with a set number of launches per year allowed. And our contract would provide customers with our launch services within 15 days of notice. So that's a very quick turnaround. That's very efficient. And the reason we would be able to do this is because, as you saw through the diagram, we're keeping it as simple as possible and as lightweight as possible. And with that comes cost savings and less middlemen in the process to make sure that we can get it from conception to fruition. And the yearly contracts would allow us to lock in these customers that would be launching small satellites just about every year, such as academic groups and small satellite companies, academic groups like the one Richard was in when he was discovering this idea, and small satellite companies who have varying needs to get their satellites into space.
So, these are our milestones that we plan on reaching. So, this startup is very young. It's barely a year old, like it's only a few months. So, our first year, we're just trying to generate revenue, and the way we plan on doing that is by offering a very simple service. We just want to test like radiation for like space electronics, but that will require us to partner with like a balloon company and with a rocket company, and we've had a lot of progress so far. So you may have heard of Alphabet's Google Ventures program. Out of that came a balloon company called Loon, and they have a fleet of stratospheric balloons that they plan on providing internet services to rural communities. But there's the side to that, which is they have a lot of balloons. You can carry electronics that need to be tested in the atmosphere, and there's just a huge market for that. So I reached out to Loon, and they wrote back to me saying that they would consider this partnership. So there's progress, in our first milestone, we're already making a ton of progress. And as you saw, we've developed diagrams and we're in the midst of building prototypes for the platform and rocket. And the second year, we would want to demonstrate that after we connect with startups that are developing these lightweight materials. Then our third year, we would actually test it. The fourth year, we'd gain customers. And then the fifth year, we'd launch rockets. It's very ambitious, but we're confident based off of just how strong this concept is, the vitality of it. We're confident that's going to grow to this.
Precisely, and we've had strategic milestones along the way, even more detailed than the ones we've outlined here, to ensure that we're on track. And as Richard mentioned, we've gotten creative in offering ancillary services at first to generate that revenue, to make sure we have the right product at first go. So to make sure that when we do launch, it's of quality. So this is the overall market, and this is really where it gets interesting. So the overall global space economy is valued at about $344.5 billion. It's a sizable amount. But specifically, the satellite industry, if you can read a little bit sideways, is $260 billion, and the non-satellite industry is $84 billion, but specifically the satellite manufacturing
and the launch service.
And the launch services. They're all segmented together, if you can read this chart. About $13.9 billion. So that's kind of where we reside, and that's where we'd like to focus our niche at first. And there's a lot of revenue to be captured, a lot of market share to be gained in this industry, especially as we mentioned earlier, it's a bit dated in the way that we've been doing things. And it's very ripe for disruption, and there's a lot of innovation to be had in this space. No pun intended.
Space. So this is just a plot showing the number of nano microsatellites that have been launched by these very large rockets. So that's the market that we plan on capturing, the nano and microsatellites, because the companies that are making these microsatellites, they're not like, they can't afford to pay for these giant rockets. They're piggybacking on these, but they're still paying very high prices, even though they're just like they're secondary. And as you can see, you have the PSLV, you have the Soyuz. The Soyuz has been around for a really long time, and this now has to be updated with the Electron rocket. If you've heard of Rocket Lab, this is another. This is just an example of a startup building small rockets specifically for small satellites, but using the older traditional means of rocket launch. And if you want.
So this is just a bit more detailed industry breakdown. Basically, just to summarize so that we don't have to go through all the metrics together, there is a lot of opportunity to disrupt different segments within the space industry, and specifically focusing on the new space industry, which is a different twist on what some might call a bit of an archaic industry as it stands, and it focuses on this environmental focus, cost saving, and synergistic space that we're occupying. So there's a lot of room for growth and a lot of room to capture a lot of profit, and that is ultimately a big part of running a business, and that's exciting for us as well.
And one more thing, so if you note there, small launch is 4 times the sticker price of heavy launch. So what that means is small rockets versus heavy rockets like the Falcon Heavy, but provides 27 times in overall savings. So the new space economy really will thrive once more startups enter with these innovative launch technologies. Mm-hmm. So these are just, so the price of helium is controlled by the U.S. government, and as you can, this comes straight from the Bureau of Land Management, and as you can see here, these are in dollars per million cubic feet, because the big question you have to ask is how much helium are these balloons going to be holding, and that will be our next slide. But as you can see here, the 100, keep that number in mind, 119 dollars per million cubic feet. Ooh. Wait, no, yeah, next. It's a later slide.
Come on in.
Welcome.
Welcome. You're right on time. Wonderful. So we're just about to get into more of the fun stuff.
Yeah, now we're going to talk about the construction. So as I mentioned, so these rockets, these platforms, everything about the design is going to be lightweight. And this is an example of a nanofiber. It's really small at less than 200 micrometers, but very, very resilient. Hasn't reached the market yet because it's still in research phase at universities. But this is an example of a material that is in the market. It's called Miralon yarn, and they're offering it just to aerospace companies. But this is an example of such lightweight materials that have reached the market. So now I'm going to talk a little bit about other space startups that are trying new alternative means of rocket launch. So this is, let me just check. So this is a diagram from 0 to infinity. So if you haven't heard of 0 to infinity, they're also interested in launching rockets from balloons. And this is an example, a diagram of their module. It's 3 stages. First, you have the main engine. So start from the beginning. The balloon lifts this 3-stage module above Earth's atmosphere. then you have it released. The module starts going up, releases the second stage, and then the third stage, and then the satellite is released. So this is an example of what they're doing. And this is something that NASA has already done. So what's interesting is a lot of the research, innovation in rocket technology has already been done by NASA. NASA's been exploring rocket balloon technology since the 1940s. This is a recent example. In order to test their Martian parachute capabilities, they decided that the most cost-efficient way would be to put the Martian rover on a rocket, lift it above Earth's atmosphere by a balloon. The rocket would then go up and release the Martian rover, and then it would deploy its parachute, and then they just tested to see how the parachute responded through Earth's atmosphere. So their main goal was to just test the parachute capabilities, but what they ended up doing was validate rocket balloon technology. And this is just another example of a rocket high launch.
Wait, I think we're gonna take a pizza break.
Oh.
You guys go ahead and get it.
So what happened
Yes.
with those NASA tests? Like they didn't launch the rover, obviously, on the balloon.
Oh yeah, so that was just them testing the capability. So they needed so this specific mission was called the LDSD. The acronym escapes my mind, but they just wanted to test how the parachute would work. So they would just bring the rover above Earth's atmosphere. They didn't plan on using a balloon.
And they did that?
Yeah, they did it. That's going to be one of the images, I think. Well, no, that's not let's go back to so this is just another example of a space startup that's exploring this technology. I'm just showing like the breadth of the number of startups that have also recognized the potential in this. And yeah, they recognize 95% less atmosphere. So there's another space club. Oh, and this is a video of a British company, like their idealization of how they imagine a balloon rocket launch. So we can just play the first 10 seconds. There we go. So it doesn't need one. Yeah. So the rocket goes on their balloon. Dramatically saving cost. Yeah, you guys get the gist of it. You just bring the rocket above Earth's atmosphere, it releases the rocket goes so much higher. I think just escape, yeah. Oh. I think we have to go to the end, right?
Maybe. Bear with us. Let's see.
Is that a helium balloon?
Yeah, it's entirely helium.
Wouldn't that cost a ton to the helium?
So the U.S. Bureau of Land Management sort of controls the price of helium, and they've set it at 119 million per cubic feet. So, and also helium is just like a byproduct gas, and there's a ton of it. It's just there's no economic incentive for really keeping it, because you're mostly using helium for hospital equipment, cooling purposes. But for the NewSpace industry, if helium becomes a vital part of it, costs will go down because they'll be capturing it more. So this is just an example. there's a company, a defense company called Raven Aerostar, and they've been developing these really large zero pressure high altitude balloons that use helium. And you can see just in the plot below, just the sort of one-to-one ratio, like you can see how balloon weight corresponds to maximum payload, and also just the volume. So you can see your maximum cubic feet at 54,000. You can, like, your balloon will weigh 13.6 pounds, but you'll have a max payload of 49 pounds. And that's just another. Oh. So these are some pertinent issues that do need to be addressed in this field. These questions come from research and like reaching out to NASA scientists. The first one is cost. So the question becomes, are you going to be using the same balloon the entire time, or are you just gonna like let it go to waste? So, you know, the balloon should, like, there's a lot of plastic involved, and the balloon would be reused. We look into like technology on how to make the balloon reusable. Because this goes into our second issue, weather. Balloon, just like you can't really predict the weather, you can't really predict wind. And balloons are very reliant on wind, and that's why you would need this balloon to be launched above an ocean, because if it falls, you know, it's not falling over a small town or any of that. Then reliability, that goes into the question about weather, because if the wind, you know, is strong enough, it could break the balloon, but we'd be able to, like, we'd choose an area with the calmest atmospheric conditions, because, you know, that's how it would work. Like, you can launch it over Antarctica, and that would be helpful. So the next one is helium. Specifically, this NASA scientist we spoke to questioned, you know, price, because are we going to be reusing the helium, or is it just all going to go to waste? And we also are looking into a method of just reusing that helium. So you'd have tethers that connect directly to the balloon to not only like keep it somewhat stationary, but also like keep the helium flow through it. Now your payload, how much, like, you know, there's a weight limit obviously, but as we saw in the diagram before, we should be able, like, with material sciences advancing with lower and lower weights, we'll be able to have higher and higher payloads. Yeah. Legality. Do you want?
Yeah, so we also have to work within the regulatory framework of the airspace that we are going to be launching these balloons in. So within our cost savings, we have to factor in the regulatory costs of making sure that we are abiding by air and space law, which is actually very interesting, and I recommend some literature on that. Also, suborbital tourism and the concept of that is actually very much underway and making a lot of strides. Stratospheric balloons, pseudo-satellites, scientific experiments, all going on, especially within the academic space, and soon, hopefully, within the commercial space as well. And in the U.S., suborbital activities they're all under space law, while in Europe, this distinction is not as clear. So I always liken it to accounting, how there are different, like there's GAAP in the US and IFRS in Europe. There's different space laws depending on what continent you're over. So navigating that as a US-based firm, but also making sure our breadth reaches all consumers who would be interested in our product is something that is really interesting and that we're working towards, and also that we're making sure that we outsource advice and gain insight from different perspectives on as we build out our platform.
Oh, yeah, so that's repeat. So now we'll talk a little bit about the history of high altitude rocket launches. So I mentioned before that NASA has a long history of just developing rocket balloon technology, but for other means. So this is a diagram from the Viking mission of the 1960s. So NASA, this is like also an example of NASA testing out the parachute capabilities of Martian landers, except this is an instance of them testing out parachute capabilities for moon landers. So they wanted to land a probe on the moon, and they wanted to see how their parachute would be able to survive just intense conditions. So they assumed, okay, if it can survive Earth atmosphere, then it should be able to survive a moon condition. So this is an example of the Viking probe. This is just a diagram of how they expected it to be released and then land on the surface. Yeah, so just a little more detail on the landing part. More of the land. So yeah, NASA was very, very detailed in their diagrams. They really wanted to have a thorough understanding, like show to other scientists that this is very possible. As you can see, you have your entry, and then once it's through the harshest part of the atmosphere, the edge, it then can deploy its parachute.
Absolutely. And as a satellite company, you're always mapping out best case and worst case scenario. And these diagrams are examples of how we make sure that we account for any unexpected or expected case scenario, things that might happen along the way.
So now I'm going to talk a little bit about Earth's atmosphere itself. So it has many layers, the troposphere, the stratosphere, the mesosphere. So the thermosphere is, most, but what the rockets really have to account for is the troposphere, because it's the densest part at the bottom, and the stratosphere is where most of the most intense weather is going to be, and has to leave that. So your balloons need to take into consideration everything. That includes space weather. The sun produces very energized particles known as solar energetic particles. And then you have galactic cosmic rays that just come from space itself. They're just originating. Sometimes you don't even know where they're coming from. And a lot of the time, you see it can affect your satellites, but a lot of the time it just goes around the Earth because we have a magnetic field. But you still have particles break through, and it can affect your satellites just as much as it affects your balloons. This is a more vivid example of this radiation. And as I mentioned before, weather is very important. When we would launch a balloon, this is an area in Antarctica that is considered the calmest area in all of Earth. And you'd just be able to launch it there, and there'd be no wind, basically. So this is a fun picture. This is SpaceX's rocket launch above Los Angeles, or you can see it from Los Angeles, and it looks like a UFO. It scared a lot of people. But and so this is a very important image. It shows how rocket engines are designed based off of where they're launched. And as you can see in the the first image, the one on the left, the rocket, you're not using as much fuel. This is a rocket engine if it's launched from Earth's surface. But the second one, if it's launched a bit higher, in the atmosphere, and it uses more of the engine itself. So it shows, where you launch impacts the type of, how you design your rocket. You can't just take a rocket from, or that you would normally launch from the surface and bring it to space. You have to design a special rocket to launch from. So this is more detail into that. So thrust coefficient changes with respect to altitude. So this is just a little diagram on the different weights of rockets and how much each one can carry. Okay. And now we're going to talk a little bit more about the environment. So rocket launches don't usually have too much of an impact on the environment that it's in, but they do have the tendency to release dangerous chemicals, and we're not. So their rocket launches aren't frequent enough to really damage the environment. But as they're becoming more and more, as satellite companies are becoming producing more and more satellites, rockets are going to be more in demand. More of these dangerous chemicals are going to be in the environment, and this was shown during a recent case where a company wanted to create a spaceport in Canada, and the Canadian government put the construction on hold because they weren't able to answer for some of these chemicals that would be released. And the difference, for a high altitude rocket launch company is your rocket's going to be releasing any dangerous chemical above Earth's atmosphere that would just burn up upon if it even goes back to the atmosphere, or it could just be released into the space. Yeah. So, any questions?
And can you use this mic here for questions?
You want to start?
Yeah, so back on the the one where you cost, reliability, those things.
Mm-hmm.
Is it picking up?
Yes.
All right, cool. So Project Loon, I think they have the technology to bring the balloon back down. Is
Mm-hmm.
that correct? So what is your intention? Would you be how would you work with Project Loon? Would you just consult with them, or would you have to develop that technology on your own?
So if we were to work with Loon, that would first provide, Proximity with experience in a collaborative partnership. But the main goal of that is to just generate revenue by providing radiation protection services for satellite components, because something I forgot to mention was the average lifespan of a satellite in space, like one of these small satellites, is 3 to 5 years. And that is mostly because the electronics degrade, they break, things happen that they didn't expect because they didn't test beforehand. And the reason they don't test beforehand is because it's very, very expensive. There is machinery that can try to replicate a space environment, but they can basically cost more than a rocket launch. It's because you're renting out the entire system. Loon, if we were to partner with Loon, with my background in radiation physics, I could help them determine what altitude would be best to figure out, okay, once you're at this altitude, your satellite will face enough radiation, and if it survives that, you can be confident that it won't break within 3 to 5 years. And if something does break, at that altitude, the balloon will come down. You'll be able to test your electronic, replace parts. So you're not losing the whole device. You're losing the broken electronic.
Hi, thanks for doing this and making this possible. I was thinking about the nano thread that you were talking about that would hold the platform, I believe. What's the tensile strength on that, and how reliable do you think it is? Because I think I remember you saying it was in development right now. So what's the sort of purported strength versus the sort of actual strength in tests, and do you plan to continue using that to sort of stage the platform along between the two balloons, or are you looking at several other options?
So the tensile strength is it's a range. It's in one of the papers, but I can't recall it offhand. But in the paper itself, they talk about using such these types of nanofibers and developing things like the threads for a space elevator. So if you've heard of space elevators, that's basically you have something permanently stationary in space, and you can just bring stuff up and down. But that's much more ways off than just launching balloons with rockets on them, because you have to take into much more than just the weather. But you have to figure out how you're gonna you're just gonna have to figure out a lot more with a space elevator. But basically, to answer your question, the tensile strength is strong enough for them to be even considering a space elevator.
Sounds good.
Yeah.
What are the benefits of balloon launches compared to launching off an airplane? Like with Virgin Orbit and other companies like that?
Yeah, so that's a very good question. So obviously, you must have read about the recent news of Virgin Orbit launching their plane and it reaching space. So that's a big alternative method for launching rockets, and there hasn't been that much research comparing the two, but it's already a much farther step than launching a rocket straight from Earth. So to answer your question, I just have to say there hasn't been enough research into the payoff for launching rockets from planes, but it is very promising, just like launching rockets from balloons.
Yes, so I have a lot of questions. I will try to be short. Just for the non-technical questions, who would be doing the launcher? Because you still need a launcher. Are you planning to develop it, or you don't? So you will be relying on something existing with a new engine, because it will be a vacuum engine or almost vacuum engine.
Mm-hmm.
So who will be doing that?
So we develop the designs, but we'd have to work with like a aerospace company. So we've considered the major ones like Boeing, but there are lots of space startups that are considering the exact same thing, like figuring out like their purpose is specifically to create these types of rockets, and we're aiming just to discover these types of startups and partner with them.
Yeah, so at this point in time, strategic partnerships are our aim, and being very strategic about how we're going about in that development process is something that we're looking into as well. Yeah.
If I may, another question. So
Go ahead.
concerning the targets, what you're considering, so in terms of price and payload, do you already have some figures, sort of payload mass, for example, or even the size of the balloon? Because we saw that the size of the balloon that are today existing are too small, I guess. Or they don't. You're not considering 30 kilograms. I guess it would be higher than that.
We do have some in development, but for competitive reasons, we're not at liberty to share the fine details of that. But it's an excellent question, and that's what differentiates us. And they are in development and currently, getting the legal side of that as well.
Yeah, like in our research market and development research, we've reached out to tons of small satellite companies like Stratologic, Spire, Planet, and they're always very helpful to just provide what they're specifically looking for in a rocket launch. So that's what we're aiming to work around, because got to work around the customer.
So yeah, for the price point you're considering, I think in the figures you mentioned there is not the last Falcon 9 launch that was last week, I think, with the right share of 64 small satellites. I guess the price per satellite is much lower than what it used to be. Mm-hmm. I'm not sure that it had the increase that you presented with the very small launchers. If you are able to launch 60 or 70 satellites at every time you launch. So you need to be sure that you will be at the precise price point for this.
Yeah,
even for the PSLV that was launched a year ago, something like this.
Yeah, so that's a good comment. So those types of launches are very rare. For SpaceX to just dedicate an entire launch to these types of satellite deployment. In fact, the research group I'm working with currently at Vanderbilt created one of the CubeSats for that 64. So it's it's a very big thing. But what they mentioned was the pricing was still within like the tens of thousands of dollars for that, and the deployment wasn't. They just sort of released everything within the same plane. With our type of space startup, like we'd pinpoint the exact altitude they'd like to choose, and it'd be very customized for the satellite company itself.
So you mentioned taking the tether up with the balloon. The balloons can go like 60 miles up, I think?
I've been thinking more of in kilometers because everything's in kilometers in science. It's like, so the atmosphere goes up like 30, 40 kilometers. The balloon, the launch itself like would probably be around 40 kilometers. And you'd escape most of the atmosphere, 99% of it at that altitude. And then once you launch, your specially designed rocket will be able to carry much more weight, go higher, cost efficient.
Yeah, it's just interesting to visualize. So the tether would go up 40?
Yes. So that's also part of, the space elevator type concept. Your tether would have to go up that high. But, like realistically, like these types of tethers already exist on Earth. You have ropes that are really long. It's just that type, except it's vertical instead of horizontal.
You have a question?
So, like in one of your slides, you had a pretty, you had a graph that showed pretty much like maximum altitude per like volume of helium per balloon, and that graph had like weight numbers on it. So, which implies that this system would probably have a very, very like strict weight like limit just due to sheer physics. And so in that case, which also means that there was a very strict limit on fuel. What kind of launch capabilities are you thinking in terms of like greater than Earth, like geosynchronous orbit, polar orbits, like which different altitudes? Like, are you only be focused on like lower Earth orbit that with satellites that burn up quickly, or are those numbers indicative of capability of reaching higher orbits?
So we're focusing mostly on low Earth orbit because low Earth orbit goes up to like 300 kilometers, and that would be the sort of maximum of what any rocket that we're considering would be able to reach from these like 30 kilometers.
So have you considered using hydrogen as a lift gas?
We've mostly looked at helium because that's what the that's what the balloon companies that we've done research into have been using. And also, I did ask one NASA scientist about it, and he explained hydrogen was too dangerous because of the explosive properties of it.
Being a rocket.
Yeah. Explode.
So right now you guys are all part-time. Do you have a roadmap to when or what condition you would meet to start flipping over to full-time? And are you guys going out and trying to raise money, or is it this side project status until you get to the point where you start getting orders or something like that?
That's a great question. So we wouldn't necessarily describe it as like side project status. I'd say it's something that we're doing in conjunction with what we're also working on in our daytime with grad school and our full-time jobs as well. We don't have a specific timeline per se. We have caps of how long we'll stay in one phase, but we do have revenue guidelines. So depending on what revenue markers we reach and how quickly we're able to accelerate, then we're able to fund certain next steps, and then we can scale.
You guys using your own money for the development right now?
Yes.
It's always good, from a finance perspective, it's always good to know that there's equity into an investment, because that means that the owners are going to do everything they can to make sure it's a success. So it's always a good investment. Any other questions? With that, thank you so much for your time. This was an excellent discussion, and if you have any questions, we will be passing out our email, and we do also have our website, proximitE.space, and we're always happy to connect and provide any more insight. Thank you.